All right, we're going to look at how waves interact. So we're going to look at interacting waves. When two or more waves interact, they will combine to form a resultant wave. So if there's interference, they will combine. Now, how we figure that out is something called the principle of superposition. So a resultant wave is simply the sum of the individual waves that make it up. So for example, two waves coming in this direction, they meet each other. When they meet, since they're both pointed in the same direction, when they meet, this wave is going to take on both crests, which means that the interference is going to make a larger. Okay, this is called constructive interference when the wave gets bigger and the waves continue on their merry way. All right, so when they interfere and the wave gets bigger, so the amplitude raises, it's called constructive interference. Now we have two waves that are out of phase, one up, one down, one a crest, one a trough, and when they meet, they combine. When they combine, we get a flat line. This flat line is when the resultant wave is smaller than the two waves that make it up. We call that destructive interference. So when they come together in phase, both crests or both troughs, they make constructive or a bigger wave. When they come together as a crest and a trough, they cancel each other out, and we get destructive interference, and we get a smaller amplitude wave. Since waves add, is the resultant wave always larger than the individual waves that combine? Of course, the answer is a big no, because you can have destructive interference. All right, so never think of that always. Just because they combine does not mean you're going to get a bigger wave. So constructive interference, when they combine to form a larger wave. Destructive interference, when they combine to form a smaller wave. So let's say we take a look at two waves like in water, like we have a drop here, right? So we drop, and constructive interference occurs where crest meets crest, so where the lines intersect. Destructive interference occurs when a crest meets a trough, and so you can see where they're not going to be together. Okay, so when we talk about water waves, that's what we see. Okay, so another type of wave is a standing wave. It's a wave that moves along a fixed location. Remember our fixed waves. There are two things on a standing wave. You have nodes and antinodes. Nodes are what doesn't move, and antinodes are where the maximum displacement, so where the maximum amplitude is of the wave. So here's an example. This is what we call the first harmonic, all right, or the fundamental harmonic. We got the length here, right? This is the length of string. It has one antinode and two nodes. Okay. Second harmonic has two antinodes and three nodes. Third harmonic has three antinodes and 1, 2, 3, 4 nodes. So when we look at these different types of waves being formed, harmonics are based on the number of antinodes, okay, or the number of highest amplitude points. All right. So second harmonic is the distance of one wavelength. The first harmonic, right, is here, and then the third harmonic would be considered 1.5 wavelengths. So here's how we find the first harmonic of a standing wave on a string. The wavelength is 2 times L. All right, so we're going back. L for the first harmonic is just the length. The second harmonic is actually 1 wavelength in distance. So 2 times L, 2 times the length of our string. Frequency is wave speed over 2L, or over the wavelength. So the fundamental frequency is V over 2L. And that, of course, is going to be in hertz for that frequency. Frequency of wavelength, meters. So, in any standing wave, the length of the string times 2 is the wavelength. Wave speed, or frequency, is wave speed over wavelength, or wave speed over 2L. So here we go. We got a string is 1.3 meters in length. It's oscillating in the first harmonic. The frequency of oscillation is 7.8 hertz. What is the wavelength of the first harmonic? So A, the wavelength of the first harmonic, and B, what is the speed of waves on this string? So the wavelength of the first harmonic, we said, is 2L. So we just take 2 times 1.3L, and that is 2.60 meters. So the wavelength, 2.60 meters. To find the speed, wavelength times frequency. Since we solve for wavelength, we just take 2.6 or 2L and we multiply it by our frequency of 7.8. And we get a speed of 20.3 meters per second. And that's the speed of our standing wave. Okay? So first harmonic, we can find wavelength, and we can find speed. So how does this apply to instruments, right? I mean, you take a look at musical instruments. We can control, this is the overall length of the string, but we can control with the frets our actual wavelengths or our harmonics. And if you play an instrument, or if you've played a string instrument, the movement of the fingers then will control our wavelength. Okay, and that's what we call them. And then harmonics, the term kind of goes along with music, harmony, and that's because of this. Okay, so you got the fundamental frequency, then you have the first octave, the second octave, and so forth. Those are terms that, if you know music, you know them. If you don't sweat it. I'm not going to ask you about octaves too much. Just know they exist.